Let's revisit the concept of field. So, final exam question. Explain the term field. What is a field in general? Talk about specific kinds of fields. What do we mean when we talk about fields? Can you answer that question? If you ask me to explain, I would start by distinguishing fields from particles. Particles are objects that have well-defined locations in space. They have well-defined boundaries. They exist as individual, discrete entities. Fields are spread out in space. You can talk about the value of a field at a point, but a field by definition is a quantity that fills space. The very word field means space. So, from a physics point of view, nature or reality is made of particles and fields, and they're different from each other, but they are related. The next step in understanding, I think, is to think about the different kinds of fields. What are those quantities, those field quantities that fill space? Well, there were scalar ones. We talked about them earlier. Temperature, pressure, density, and vector fields. Well, naturally, electric, magnetic, wind velocity. Those are quantities that we give the values throughout space, and that describes the field by those quantities described over space. So we learned this semester that we can't think of a particle, a charge, simply as a particle with a positive charge or a particle with a negative charge. How do these particles interact without touching? The way they interact is through their fields. So this particle has associated with it a field, and we represent or picture that field through field lines. But the field lines are just a pictorial representation. The electric field of this positive charge fills the space around it. And we know how it fills it. It fills it in a way that it gets weaker and weaker as 1 over r squared, and we have an equation for calculating what the electric field is due to a point charge. But we picture it with these field lines, these arrows. And so to talk about the particle without the field or the field without the particle, we can't do it. And the same with the negative particle. So that's our electric field. And what's striking about the electric field is it has a certain look, right? We see a positive charge, we see a negative charge. And what do we see? We see field lines begin on a positive charge and they end on a negative charge. And these field lines don't end until they find a negative charge. And these field lines don't begin only when they come from a positive charge. Then we came to magnets. We learned about magnets. They interact. So magnets have fields. But we came across a very curious and very different behavior than electric fields. We saw that a magnet, which has a north and a south pole, can't be cut in half. And that we discovered by investigation that the field lines leaving the North Pole go back and enter the South Pole, but they don't begin at the North Pole and end at the South Pole. They go right through. So these field lines, very different from electric field lines, have no beginning and no end. They're continuous loops. And there are no magnets, right? We have a positive charge, field lines begin. We have a negative charge, field lines end. We have no North Pole where the field lines originate. So what did we see? What we discovered was that magnetic field lines arise from moving charge. The source is a moving charge, but they don't come out of the charge. They circle the charge. They're closed circles that surround not the charge, but the moving charge. So these fields are very, very different from electric fields. They're circles. And the way we make a dipole is we bend the wire into a loop. When we take a wire with current in it, which has closed circular loops surrounding the wire, which is the magnetic field, and we bend that wire into a current loop, what do we see? We see those circular field lines passing through the loop in a certain direction, and the net result is we get a magnetic field that looks exactly like the dipole magnet. And so a magnetic field, and then if we take the loop and we put many, many wires so that it extends through space, then we get a coil. And the coil and the magnet are the same thing. And we found out that the reason this is magnetic is that there are moving charges inside the iron that make up the magnet. So the source of field lines are moving electric charge, and the field lines are closed loops. So just step back for a minute and look at the electric field and the magnetic field. In some very simple sense, they're opposite. These things begin and end at a point, and they're radial. And in a simple case like this, they have no curvature. They diverge or converge. These things just curl in circular loops. So when you get to Calc 3, you'll realize that there's a fundamental mathematical difference in the description of fields which leave a point and diverge, or enter a point and converge, and field lines which close on themselves in a circular curling fashion. Divergence and curl. That's the fundamental difference between these two fields. And the mathematical description of that is embraced in Gauss's law, Ampere's law, actually Gauss's two laws, Ampere's law, and what we'll soon see as Faraday's law. One word of caution: electric field lines can curve, they can bend. In that sense, they curl, but they don't close on themselves. They begin and they end at a certain point. And so they have curvature, but they don't have what's mathematically called curl, Calc 3. So what we saw several weeks ago was Gauss's law for electric fields. And you should recognize this, and I'll talk about it. And what we're seeing this week is Ampere's law for magnetic fields. And what I'll talk about today is Gauss's law for magnetic fields. And what we'll talk about next week is Faraday's law for magnetic fields. And these four equations combined are called Maxwell's equations and capture the mathematics and the physics that we know about electric and magnetic fields. And when you reach Calc 3, you'll see that these can be written as we now write them in an integral form, but they also have a differential form where you use those Calc 3 vector differential designations of divergence and curl. Div, grad, curl. You'll learn that in Calc 3. So first, Gauss's law that we already talked about. Because field lines only arise out of a positive or end on a negative charge, if you draw any closed surface, if you take any closed surface that doesn't enclose a charge, then no matter what the shape or form is, the number of field lines entering will be equal to the number of field lines leaving. And the only way to get a situation where the number of field lines entering or leaving is not equal to 0 is to enclose the charge in a closed surface. So I think the best way to explain Gauss's law is to draw a picture of a dipole. And no matter what closed surface I draw that doesn't enclose a charge, no matter what the shape is, the number of field lines entering and leaving will always equal 0. And if I enclose the charge, no matter how I enclose it, with a small surface or a larger surface, the number of field lines leaving that charge will be exactly equal to the charge inside. And if I only enclose half the charge, the number of field lines leaving will be positive, but they will be half as many. And the same way with the negative charge. So if I draw a surface here, I get nothing. But if I draw a surface that encloses the negative charge, no matter what the shape, if there are 16 field lines leaving this negative charge, then no matter what shape the surface that encloses it, there'll be 16 field lines. And if I draw a surface that contains half the charge, then 8 field lines will enter. And so by simply counting the field lines or doing the integral of E dot dA over the surface, it will always equal to the charge inside divided by epsilon naught. Now, if we go to magnetic field, in a magnetic field, since the field lines have no beginning and no end, that means that no matter what kind of a closed surface you draw, let's enclose space. We see 3 lines entering, 3 lines leaving. But even if we enclose the South Pole, we see that the number of lines entering equals the number of lines leaving. And no matter how you draw the closed surface, no matter what surface you draw, because the lines are closed, they can't end inside, they can't begin inside. Whatever line enters has to leave. And so that leads to Gauss's second law. So, right, if we do this integral over a closed surface and the charge is not enclosed, it will be 0. Positive charge will give us a positive integral. Negative charge will give us a negative integral, like counting field lines. If we do that for a magnetic field, no matter what the shape or location of that closed surface, this integral of B dot dA, the flux through a closed surface, will always be 0 because the lines do not originate or end anywhere. So number 3 on this list is Faraday's law, which we'll discover next week, but the law, Ampere's law that we want to discuss this week, can be seen here. And when you see it, often in textbooks or places, you'll notice that there's an additional term called the Maxwell term. So Ampere originally wrote it that this is equal to this, and that's how we'll use it. We won't talk about this additional term in this semester. So Ampere's law, mathematically, by calculus, is a line integral. And the ds represents a line, any line, but it has to be a closed loop. So in Gauss's law, we drew closed surfaces. In Ampere's law, we drew closed Amperian loops. And if we do the integral of B dot ds around that closed loop, we'll find out that it's 0 if no current is enclosed, but it will have this value if we enclose current. So it's similar to Gauss's law in that you only get a positive answer if enclosed in the loop is a amount of current, a positive amount of current. And this term, again, we're ignoring for the time being. So I just remembered there's an entire video on Ampere's law, so I won't talk about it here. Only let's just, before we close, let's summarize and capture the highlights of what we discussed. Electric fields are fields which have sources. They have a place where they begin and a place where they end, and they never form closed loops. Magnetic fields never begin or end, they always form closed loops. So from a calculus point of view, these kinds of fields have divergence. But they only diverge if you enclose the point from which they originate. So there's no divergence out of this surface. And that's captured in Gauss's law. But they have no curl. So you'll see when we talk about Ampere's law, this field, if we do the integral of E dot ds, it'll always be 0. Just like the integral of B dot dA is always 0 for magnetic fields, because these fields have curl and no divergence, and these fields, from the Calc 3 point of view, have divergence but no curl. So the simple takeaway is think of magnetic fields in this picture and this picture, and notice how starkly different and the contrast between them.